Start as soon people sit down.
These are the buses from the other project.
Okay, let's take 2 minutes.
It's okay, it's okay.
Okay, so let's get started with our calorimetry session. Welcome everyone, and we will start by Fabio Appacher to talk about the commissioning of the Mu2e calorimeter.
Thank you. Good morning to everybody. Yes, I will show you the design and the construction status of the Mu2e calorimeter. The talk outline is as follows. I will touch briefly the measurement overview of the experiment and the technique of the Mu2e experiment. I will show you what are the requirements for the calorimeter, and eventually that drove the technical choice and its design. We'll indulge a little bit on the calorimeter engineering design and its integration. I will show you the calorimeter performances as measured in beam tests and prototypes. And then I will show you the production status of all the main components that are crystals, photodetectors, front-end and digitizer electronics. I will show you the status of the mechanics, and we will conclude with some assembly plans that actually are taking place very soon. So briefly, the Mu2e experiments aims at the measurement of the charge lepton flavor violation process, that is the conversion of a muon into an electron. Here you see bound in an atom of aluminum. Here you see a picture of what we are looking for. For this process, we have a very clear signature that is provided by the monoenergetic electron conversion that has an energy of the mass of the muon. And the proton beam of Fermilab is going to produce a very high intensity pulse beam of 10 gigahertz of stopped muons. The goal is to reach single event sensitivity 4 order of magnitudes better than syndrome 2. Mu2e will detect and count the conversion electrons with respect to the standard muon capture. The main background is the standard model decay of the electron bound to the nucleus of aluminum into an electron and 2 neutrinos. Here you see the spectral distribution of these two processes. Here you see the theoretical monoenergetic line and the Michel spectrum of the DIO shape. Of course, resolution effects makes these events entering the signal window. And therefore, we need to have a very, very good resolution in our detectors. So, from cartoons to reality, the spectrometer of Mu2e is a very complex system of solenoids. We have three solenoids: the production solenoids, the transport solenoid, and the detector solenoids. So the production solenoids, that is, has a graded magnetic field from 4.6 Tesla to 2.5 Tesla, is being hit by the proton beam that actually hits the tungsten rod target. In this process, we have a lot of pions produced as secondary particles. These pions are somehow funneled, focused back, thanks to the graded solenoid system, into the transport solenoid, where they eventually decay into muons. These muons are charge and momentum selected. The muons enter the detector solenoid, where they hit the aluminum target, and eventually the muon that is stopped into the aluminum converts into an electron. Here you see the helix path of the electrons, the conversion electrons that eventually hits first the tracker, and then the calorimeter. Here I show you the status of the art of the construction of the three main solenoids, the production solenoid, the transport solenoid, this is the one in better shape, and the detector solenoid. So the requirement for the calorimeter is that in this search, the calorimeter has to have redundancy and complementary qualities with respect to the king of the detector, that is the tracker, the straw tube tracker that has a very, very precise resolution to eventually measure the conversion electron. So, but the calorimeter is going to add additional seeds to improve track finding. Also, is capable to reject muons from electrons. And in order to fulfill these requirements, the calorimeter has to provide an energy resolution of the order of 10%, time resolution of the order of 500 picoseconds, provide a very good position resolution to be able to add track finding. Everything is in vacuum inside a 1 Tesla magnetic field, and also there is a harsh radiation environment. So here I show you that the reason why both the tracker and the calorimeter have an hole inside, because we don't want to detect low momentum particles, but we only want to detect particles from 80 MeV to up. So the technical specification to fulfill the requirements that we just talked about are, so we decided to build a high granularity crystal calorimeter with CPM readout. So eventually the geometry is going to be 2 annuli to improve the acceptance. The crystals have to have a very high light yield in order to have the best energy and time resolution. At least we need to have, we evaluated to have 20 photoelectrons per MeV. We are going to have 2 CPMs and preamps per crystals. Also the CPMs need to be thermally controlled down to -10 degrees in order to reduce eventual radiation-induced leakage current. We also need to have fast signal, fast digitization for pile-up disentangling and timing resolution. And the crystal, and all the main components in the core of the calorimeter needs to withstand a lot of radiation and neutron fluence. So eventually, the design of the calorimeter is as shown in this CAD picture. So we have two annuli. Each annular disk is containing 674 undoped CSI crystals with these dimensions. Each crystal, as I said, is read out by a custom-made CPMs coupled in air. Of course, the PDA is maximized at emission light of the crystal. Also, the crystals are Tyvek and Tedlar wrapped to maximize light yield and minimize the crosstalk. The CPM are glued into these holders and directly connected to onboard front-end electronics. On top of that, we have 200 megasamples per second digital electronics on custom crates. And both disks are also instrumented with calibration systems. There is a radioactive source ALABA bar and a green laser system that provides absolute and gain monitoring capability. So this is an X-ray, an exploded view of all the components of the calorimeter. We have an outer monolithic aluminum supporting discs, actually for each disk. Then we have an inner low-budget material, it's carbon fiber inner ring. And then we have two covers, a front cover that is also housing the piping for the source, and also a front-end electronic plate that is housing this holder that has the CPMs and the front-end electronics. All this is instrumented with cabling and pipes, of course. So once we froze the technology of the calorimeter, we built a Module 0 prototype that somehow has actually all the final premises, chosen technologies. So this Module 0 calorimeter has been tested at the BTF in Frascati. And the energy resolution and timing resolution that we obtained for 100 MeV electrons is well in agreement with the requirements. Here you see when we were assembling the crystals, controlling the moisture, of course, and here is the module 0 sitting in the BTF facility. So these are the results we obtained in the BTF. And so, as you can see, we had a very good resolution, energy resolution, ranging from 5 to 7% according to the angle we were impinging the calorimeter. And the resolution is of the order of 100 picoseconds. So the results fully comply with our requirements, and this gave us green light for the purchase of the components. So we started with the most expensive and most long-standing procurement of parts that were the crystals and the CPMs. So we had two producers for the crystals, SICAS and Saint-Gobain. As long as the crystals were coming to Fermilab, we were testing them for both for optical and mechanical properties. Unfortunately, Saint-Gobain failed to match some specification, and we needed to give back Saint-Gobain tender to SICAS that eventually produced almost all the crystals. So these are the results for the light yield distribution of the and for the crystals and the energy resolution. So the production of the crystals is completed. The CPMs are custom-made Hamamatsu CPM, are 6 individual cells connected as in this sketch. Also for the CPMs, we measure breakdown voltage, dark current, the gain, and we also have irradiated them, sampling 5 CPMs per batch, and these are also the results of the tests. So we did reject a very little number of photosensors. So with the photosensors in our hand, we could assemble this delicate part of the calorimeter that is the readout unit, is an old photomultiplier. So we are gluing the photosensor into this copper holder that also will contain the front-end electronic boards, a Faraday cage, a fiber needle to calibrate each individual crystal. Here you see the gluing procedure was a tedious procedure where we thought of doing at Fermilab, but for COVID reasons, we had to move everything to Frascati, shipping back and forth stuff from Fermilab, and do the gluing in Frascati. So now we have everything ready, and we are assembling and testing these readout units. And this is going to be shown by Elisa in her poster. So the CPM signals is fed to this front-end electronic board that consists in a transimpedance preamplifier, a shaper, and a voltage regulator. Then the signal is sent to these 10 DAQ crates where we have mezzanine boards that take care of the slow control distribution and high voltage, low voltage setting, and are paired, as you can see here, to the digitizer that is a 200 megasample per second board with a 12-bit ADC flash ADC. So of course, the sampling is optimized for signal reconstruction and pile-up disentangling. But Franco will show much more details on this. As soon as the first board, mezzanine boards and Dirac boards were being produced, we decided to have a calorimeter vertical slice test with Cosmics in Frascati. So we use our vacuum vessel that we built on purpose to test the full functionality of the module 0, including the ability to cool down in temperature the CPMs. Here we have a crate, a real crate, that is housing the mezzanine board and the digitizer. We also use a custom-made cosmic ray tagger to tag muons. Here you see, and Ruben will show many more details on this in his poster. Here you see the Mip charge distribution. Here you have a crossing Mip in the calorimeter. Here are some summary of the results. We have a very good level of noise. Then our students are playing around optimizing the construction of the template to fit energy and time resolution. Here you see the Mip signal is a very robust 400 millivolt signal. And we also exercise in T0 finding And here you can see the time distribution, the time resolution obtained with Cosmics that it gives us a cell mean time resolution of around 200 picoseconds. So it's already very good with MIP. So as I said, we have two calibration tools, a source and a laser system. The source is composed by neutrons from a DT generator. It's coming from Babar, and our Caltech colleagues are taking care of this system. Irradiates a fluorine-rich fluid that is then piped into the front phase that I was showing you. Then the following reaction takes place. And so what happens is that you have 6 MeV photons hitting the surface of the crystal. Thank you. And here you can see how well we can calibrate each crystal at the order of 10%. On top of this this source calibration system, we have a laser calibration system. Here you have a laser bench with pin diodes for monitoring the stability of the laser shine, and a fiber system to and the integration sphere to route the light to each individual channel of the calorimeter. That this system is going to keep the stability at the level of the percent. So where we are, this is the mechanical parts procurement. We have almost of the parts, apart from this sandwich that is made of carbon fiber, aluminum honeycomb that is like a pillow where the source pipes is embedded, that is being built as we speak. And we think of getting it by the end of the month. So we have produced all the fit, we need to assemble them. We have the outer aluminum ring. This is the one that is already at Fermilab and is waiting to be filled with crystals. We have these two very nice pieces of engineering that are the front-end electronic plates made in PIC with all these cooling lines in copper. Then we have the inner ring that was tested, stress tested in Frascati with lead loads. And the crates are also ready, as you will see in the next picture, where we exercise with all the mechanical parts that were produced, and we made some dry fit. So we first paired the front-end electronic plate to the outer aluminum ring. Then we added the cooling manifolds to the crates. The crates have cooling lines as well. Then we added also the first inner carbon fiber sealing that is being measured as we speak. Here is a cabling mock-up exercise. Here you see people at welding the pipes. So, as I said, almost everything is ready, and we have, actually, yesterday, the first big crate left Frascati towards Fermilab, where we are going to receive it in a couple of weeks. So the conclusions of the status of the construction of the calorimeter are as follows. So we think that the technical choice shows a good energy resolution and timing resolution, and we tested it. The most demanding requirement was to operate in the magnetic field, in vacuum, and in rad-hard environment. Anyhow, CPM work under neutron radiation, but eventually need to be cooled down. The engineering of the cooling was challenging. So, as I say, the production of the crystal, CPM, front-end electronics is completed. Also, the mechanical part is completed. The vertical slice test is promising, and we are keeping producing the digitizer board, and we are shipping the material. So the plan is to start assembly, first outgassing the components, because the components, before getting assembled into the disk, need to be evacuated, not to load into the vacuum, the cryostat vacuum. And so we plan to begin the crystal stacking June, July. And eventually we will be moving the two disks in the Mu2E hall by the end of the next year. And I'm done. Thank you.
Thank you very much.
Thank you.
Any questions?
Over there.
This question there.
Thank you for the nice overview. Can you say a little more on the cooling? So you control the accuracy, or you still need to correct for gain variation with
Yes,
temperature?
you answer, and you also you ask your question, you also answer it. Yes. Anyhow, the most delicate part. I mean, the crates, you just have to dissipate the heat produced by the electronics. The complicated part is the thermalization of the CPM. That is very complicated. But I mean, the heat load is such that they will eventually be stabilized, but we also monitor the temperature, and we know how much we should correct for monitor changes, for temperature changes.
Okay, one more question there.
Hi, good morning. Just
Ciao.
curiosity, why the coupling between the CPM and the crystal is made with 2 millimeter air? I understand.
The best way, yes, that's nice. I mean, the best way, it's for mechanical reasons, but I mean, the best way would have been to put some optical grease, but we are in vacuum, so optical grease outgasses. So we could have connect directly the crystals to the CPM, but then we get back to this question, because since the CPMs are cooled down, you don't want to transfer to cool down also the crystal. So eventually also the crystals will be cooled down a little bit, but as long as there is no gradient in the temperature along the crystal, that's not a problem. But it's going to be a dynamic process. I mean, you cool down much more fast the CPM part and the front plate disk, and you want to think about it as detached as possible from the rest of the mechanics, not to have a heat load that is too unbearable. Okay?
Okay, so thank you very much. Thanks to the speaker again.
Thank you.
So our next speaker, Torben Quast. So let's hear now about the CMS high granularity calorimeter.
Yeah, in particular about the timing aspects of this calorimeter. So from Fermilab, we're going back to CERN, and as we've heard already at multiple occasions, the testing of the standard model at CERN will continue until the end of the 30s, beginning of the 40s even. And yeah, currently we have accumulated the data set of about corresponding to 4% of what is ultimately accumulated. Now with run 3, we want to double that. And then at the end of the 20s, beginning of the 30s, we will have the so-called high luminosity LHC, where we can ultimately accumulate the data set corresponding to up to 4 inverse autobahn. But before getting to this fantastic data set at the end, we need to first upgrade the Large Hadron Collider, and correspondingly also with it the LHC experiments. So in particular Atlas, CMS, LHCb, and Alice. Looking at CMS, there are many upgrades foreseen before high luminosity LHC, and we have heard yesterday from Alessandro about the tracker. There's also more upgrades for instance, the barocalorimeter, for the muon system and others. So for instance, that's supposed to become a Mip timing detector, for which I've seen a poster. And what's going to happen with the end cap calorimeters? This is something very drastic, because the existing end cap calorimeters will really be taken off with the SAW, and will be replaced with something completely new. And this completely new is this fantastic high granularity calorimeter. Very ambitious project because of its sheer size. GCal, it's its abbreviation. In essence, it's a sampling calorimeter, which will have silicon and scintillators as sensitive material. Silicon in total, we have an area of more than 600 square meters. So luckily, we already procured the silicon before the shortage of the semiconductor material worldwide. We have a similar order of magnitude of scintillators, which we will equip in the outermost region where the radiation levels allow. And yeah, the name-giving feature of HGCal is the readout, the size of the sensitive units. So the size of the sensitive units, in particular in the very forward region, in the silicon region, corresponds to the size of my thumb, or my small finger. So half a centimeter to a full square centimeter. And yeah, we will have at the end more than 6 million of channels, which will all give, as a function of the position, an idea of how much energy has gone through this sensitive unit, and ideally also the time, which I will hint at. So the idea is that HCal is in fact an imaging calorimeter. So the idea is that you are supposed to be able to see by eye what's sort of happening inside your detector. And here, as an example, I brought with me a simulated Higgs boson created from vector boson fusion. That Higgs boson is supposed to decay into two gammas. The gamma and the two jet by chance happen to go into the same quadrant of one of the end caps. And you can really see here, for instance, really the jet evolving. This is here in yellowish throughout the full layers because it has hadronic components, so it goes through the full calorimeter. And also the photon you see in the very first layers. All the stuff around is, parts of it still belongs to the signal, but most of the things, most of the hits actually corresponds to PIlab. PIlab for high luminosity LHC will be one of the most drastic challenges that we will have to cope with, because currently we have order of 40, 50 PIlab interactions per bunch crossing. Well, at high luminosity LHC we will have 140 to 200. So it will be quite challenging to make sense of what actually happened, what is your interaction of interest that you actually want to analyze. And this is even more obvious if you take the same event that we looked at before and project all the hits, all the energy into one plane. You really have to look closely to find out what you actually want to see. Of course, you can now make a career out of making sense of all such images by writing dedicated software and using machine learning, and all of this is nice and it works to some degree, but what you also need to have timing. So you need to have like some segmentation in the fourth dimension. And this is also illustrated here in this simulated event. So if you assume you have a timing resolution of 20, 30 picoseconds, and you can then reconstruct what the timestamps of these clusters is, which you say this is my signal, and then you basically select all the hits which are sort of in the vicinity in the time domain with respect to these two clusters, and by this means you can reject lots of the PIlab. So that's basically what timing is there for. At the time of when HCal was proposed and when the technical design report was written a few years ago, these studies based on simulation have been done extensively. A timing resolution of about 20, 30 picoseconds, as I said, was assumed. I do not want to quote too many of these studies because they are by now a bit outdated because the design of the detector has changed a bit. But these two plots are still, in my opinion, still hold. So the left plot illustrates nicely the feature that was shown on the slide before. Namely, if you have a good timing resolution and you cut basically the tails out, you can reject most of these red and blue here, which correspond to the hits of the timing of the PIlab. And also you can reject really vertices which do not come from your main vertex. So here in black, this is the hits coming from an interaction happening really at the 0, 0 of your interaction of interest. Red are hits from an interaction further away, 10 centimeters, and of course this then corresponds to a time of flight of a few hundreds of picoseconds, and if you have 20 picoseconds of resolution, you can nicely separate that. Another prediction which was done at this time is that you should have at the order of 10 to 100 hits with a timestamp at the end, and if you combine these timestamps for, let's say, a cluster, so for a single particle, you should have an order of 10% at not 10 picoseconds resolution for full showers in timing. So this is what you can expect still. Achieving such a resolution is not trivial at all because you have all sorts of sources where sort of the resolution can degrade, and it starts obviously with a silicon sensor. So the signal formation in the sensor that you're using should be fast enough, and this has been studied for our silicon sensor prototypes in test beam already in 2016-17, and there we could demonstrate that the asymptotic time resolution for silicon is for our silicon sensors is indeed 10 picoseconds. Then you have many contributions from the actual readout ASIC, from the readout electronics. So you have a term from the preamplifier, you have time walk, you have the TDC binning, etc., etc. And of course, all of this is most likely dominating your time resolution, and in fact, getting a good ASIC that is able to get your timing resolution is key. Of course, another aspect is the clock distribution, which can also then sort of deteriorate your time resolution. And maybe in 10 years from now, there will be another person who can talk to you about how this was actually controlled and how this was calibrated in the final system. What I can tell you today is how we did this in the test beam by now 4 years ago, so 1 year before Corona. So what we tested at the end of 2018 was a prototype system from HCCAR, where we had a prototype readout ASIC, the so-called Skyrock 2 CMS. The Skyrock 2 CMS had a prototype circuit for the time of arrival measurement, for the timing measurement. Basically, you had there a fast shaper followed by a discriminator, and then you had a block which then converted the time to an amplitude, and this amplitude then gave you an insight of when the incidence of the time was. What we knew from characterizing this chip beforehand is that we could expect an order of 50 picoseconds time resolution for this chip. And as I said, we have constructed modules with these chips, with prototype silicon modules. We have already published some of these results. And one of the unpublished results yet is something that I will have here. That's the validation of the timing performance of the system. So what we used for measuring the timing and for calibrating the system was a reference detector, reference timing detector, as we have seen also yesterday, and also various posters, these microchannel plates. In our case, we had their contribution of about 30 picoseconds. So this is what one should, of course, keep in mind when measuring such a thing. So this is here an illustration of what sort of timing information we had available at the test beam, and this can also be, to some extent, representative to what will be in the final system. So we had here the microchannel plate system, which gave us the waveform, and with a simple waveform analysis, we could then extract the time with respect to the clock. Then, the particle propagated further through the detector, eventually reached the individual readout channels, where it was then triggering the TOA, the time of arrival ramps, until the next rising and falling clock edges. And then the strategy was simply for the calibration to compare the timestamp from the MCP with the TOA and all its the reconstructed energy of each readout channel. And what you then end up with is a 2+1 calibration procedure. So the first step is obviously the calibration of the TOA. In this case, we have a nonlinearity because of the TAC ramp up. Then the second, so and here the order is of course 25 nanosecond, covering the full clock period. The second term is also what was expected because we have a constant threshold discrimination, is the time walk, which in our case, this is here 3.5 nanoseconds, that's the scale. So we have orders of 1 nanoseconds here, that's the scale. And then the last term, which was a bit unexpected and which illustrates the importance of doing such test beams and such prototype tests, was actually a correlation of the time with the total energy that was deposited in one of these modules, which we interpret as a sort of baseline shift, which then affects the time, the measured time. And this is also at the order of hundreds of picoseconds, is what we saw in the data. But yeah, if we had enough data, enough statistics to calibrate at the order of hundreds of readout channels, and having all of these calibrated, we could for the first time make such nice event videos. So we can really make videos of how, in our case, positron goes through the detector. And this is here illustrated in 3 time frames. So this is here the first 400 picoseconds, the second 400 picoseconds, and the last 400 picoseconds. And also color-coded is also here the order of when these hits were created. And you can really see by looking closely, you can really see this video feature. So this is quite nice. So looking a bit more detailed in what we have measured here in terms of the timing performance. So by comparing the timestamps from representative readout channels to the MCP, we are getting sort of at the order of 70 picoseconds at a reference energy of 800 MIPS. So that's an intermediate energy, which is representative for 300 GeV positron shower. If we compare the timestamps between 2 readout channels, having multiple, although you can do this exercise, you actually get a bit better. And you also see that readout channels from the same module also seem to be correlated, which was also not really expected, but it's not too bad. It's not too surprising because you have the same sort of phase space of your calibration. Anyways, there's a small discrepancy between what you get here by comparing channels to channels and channel to MCP, 70 to 55 picoseconds, and we attribute this feature to a global jitter between the HECAL or prototype readout system and the system which read out the MCPs and where we injected the copy of the clock. Unfortunately, we were not able to reproduce this feature, but we are quite confident that this is the case, and you can see it quite nicely here. So what you're seeing here in each bar is for each readout, for each shower that went through the prototype, the distribution of timestamps with respect to the MCP, and you can see that the timestamps themselves, they're quite consistent with each other in HECAL, and they are commonly shifted with respect to the MCP. So that really hints at the presence of such a global jitter, which is between these two, between the main system and the reference system. Quantifying this a bit further, what we can do here is we can compute a global shower timestamp. So by combining all the hits from a shower and comparing it to the MCP, this is here shown, the distribution of this exercise is shown in blue. You get then to a resolution of about 56 picoseconds. And if you do the same sort of exercise, but only taking odd and even layers, so always 14 layers of your prototype, and compare these two timestamps, you get to a resolution of about 36 picoseconds. And by then doing a bit of algebra and considerations of how these resolutions can come up, we are sort of confident that this global jitter amounts to about 50 picoseconds. And if we then take this global jitter and we subtract it from our data, we get really to a shower timestamp resolution of less than 200 picoseconds. And the good thing is, this is another cross-check, we are able to reproduce this feature in Monte Carlo by injecting by what we think is the true channel resolution. So that is quite nice. So less than 20 picoseconds resolution, and you also need to, of course, always show your bias, so how far you are systematically off at a given shower energy. And here, except for this low energy point at, I think this is 20 GeV, we are well within 10 picoseconds. So 20 plus 10, so that explains the title of the talk. That gives you about 30 picoseconds timing performance, let's say. So as I said, this was for prototype ASIC. We are currently in the phase of finalizing the design of the ultimate ASIC. This will be the so-called HEC rock. And this HEC rock will have a completely different TDC, a completely different way of reading out the time of arrival. The good news is that there have been laboratory tests already with this newest design, the so-called version 3. The time walk is still as expected, and the resolution that was measured for this particular chip is not 50 picoseconds as it was for the Skyrock 2 CMS, but in fact only 13 picoseconds, so about 3 to 4 times better than it. And of course, what will have to be done in the next months or years is to build full modules with these HEC rock, test them ideally also with particle beam and sort of repeat this exercise as I've shown here today, and hopefully we'll see an even better resolution then. But I think overall it's quite encouraging, but at the end I'm not able to give you a conclusion, but only a summary. So HECAL will use silicon as a sensitive material. With silicon you can also do timing measurements, so you will be able to ultimately have a 4-dimensional energy measurement with this calorimeter. And this timing resolution is important to suppress pileup. That's what we're going to use it for. You can also use it to identify the timestamps of clusters and potentially use it in analyses. But this I'm not so sure about yet. In test beam we have demonstrated the resolution of 20 picoseconds with a bias of less than 10 picoseconds for electromagnetic showers. And the final ASIC, the HEC rock, the prototyping is now finished, and the laboratory tests indicate that it's even better in terms of the timing performance. Thank you very much.
Thank you. Thank you very much. Questions?
Just as a curiosity, I mean, all these corrections are really complicated in general. But also, since you have millions of channels, what is your strategy of calibrating for example, the T0s and check them out during the data taking?
So for the test bin, that's what we had to do.
Right,
yes.
but for the experiment, you have a strategy because 10 picoseconds is going to be a number.
Yeah,
for calibration.
I do not have I cannot give you a definite answer on that, but it will be definitely challenging. Yes.
More
Yes,
questions?
Okay. There is a pretty high probability that pile-up hits would overlap with signal hit in one cell, right? So to which extent the timing resolution would degrade because of background of pile-up contribution, which precedes the signal contribution in a particular cell?
Well, this I cannot tell you definitely, but I can tell you that all these consideration was included in the simulation studies. But I mean, if you have pile-up coming a bit later, and your first signal, the interesting signal comes first, that's what you're measuring, because you're really measuring the rise time of the signal. So I'm not sure if it really degrades that. Yeah.
Oh. Well, so essentially the timing is matched by the front, right?
Yes.
And so if there are two signals, then there is one small signal and then a big, and then your signal.
Mm-hmm.
And the system could be triggered by the first small pulse.
Yes, exactly.
Right? And this would degrade the time. Actually,
Well, if the pile-up comes later, I don't see why it would degrade, but
okay.
to be honest, well, we can take this offline,
Yeah.
maybe.
Okay.
It sounds like a big project to simulate that. More questions? Is it your fault that there is no more silicon on the market?
Might be that we contributed to it. Yes.
Thanks, the speaker again. Okay, so now we will hear about shower acceleration in oriented crystal scintillators by Laura Bandiera. Somebody?
The other way around, sorry.
Okay. Good morning, everybody. I'm Laura Bandiera from INFN Ferrara, and I will speak about some measurement we have done with oriented crystal scintillator that I think are very interesting. So this work was done inside a small INFN experiment financed by the Commission 5 of INFN. It's called STORM, that stands for Strong Crystalline Electromagnetic Field, and involve some Italian team, and we have external collaborators across the world. I will briefly introduce what is a strong crystalline field and how in such field the electromagnetic shower is modified. Some experimental tests we have done on latent state sample with 100 GeV electrons at CERN SPS, and possible application in ultra-compact electromagnetic calorimeter for high energy and astroparticle physics. So in a crystal lattice, you can always recognize some strong direction. And what happens if an electrons interact, so the trajectory of an electrons is aligned with some particular crystal axis. So it suffers a series of correlated collisions with the atom in the same row. So you can replace the electric field of single atoms with a continuous string. And the results is a modification of the dynamics of the electrons that can be, for instance, channeled around a crystal axis. But also this modification of the dynamics modify the emission of bremsstrahlung radiation. This was discovered many years ago, for instance, for 50 MeV electrons. We can see here the standard bremsstrahlung spectrum, but when the electron trajectory is aligned with some particular direction in the diamond, we see an enhancement of the radiation in the soft part of the spectrum. But what happens if the electron has an ultra-relativistic energy? In a reference frame that is moving with the longitudinal velocity of the particle, the electric field of the string is Lorentz contracted, and so the effective field felt by the electron can be very high, in particular since the axial field in high dense crystal can be very high, 10 to the 11 volt on centimeter, for all the lengths of the crystals. So at beam energy already above 10 GeV, the effective field felt by the electron can reach the critical Schwinger QED field, 10 to the 16 volt on centimeter, above which the electrodynamics becomes nonlinear. But what does it mean in crystals? So because usually this field are in magnetars, can be found in heavy ion collider, interaction with strong laser or linear collider. But in crystal already at accessible energy, 10 GeV for tungsten crystal, 100 GeV for instance for germanium crystals, what happens? So these are the results of 120 GeV electrons interacting with the 3 millimeter germanium crystals. This is the energy loss measured with the calorimeter. So in case of randomly oriented germanium crystal, you have the standard bremsstrahlung spectrum, so peak around 0 and decrease with energy. But when the crystal is oriented along the strongest axis of germanium, the 110, you see an enhancement of the energy loss, peak around 95 GeV. So basically, in a very short crystal compared to the radiation length of germanium, most of the particle has lost most of their energy. So you have a strong increase in the radiated energy and also in the energy of the photon emitted that becomes harder and harder. So it's like having a germanium crystal with a reduced radiation length. So you have a decrease of the radiation length that becomes more and more shorter depending on the initial particle energy. But which is the angular, I have to be precise in the alignment with the crystal. Not so much, not so much. Because the angular range is around, goes from few milliradians, but you can see an effect even around 1 degree. So it's not so small, it's not microradians. And what is important that the angular range does not depend on particle energy, but only on the type of chosen crystal, so the Z of the material and of the chosen axis. But not only bremsstrahlung is enhancement, but also pair production. So these are the results of very high energy photons interacting in an oriented tungsten crystal. So you can see that as a function of the energy, you have an enhancement of pair production that is quite macroscopic. And altogether, you basically are accelerating the electromagnetic shower. So because you are effectively reducing the radiation length. That this reduction is dynamic during the shower because always depend on the particle energy, on the photon energy, on the electron and positron energy. But so basically, a particle that interacts with a crystal detector in which the crystals are not oriented, you have a standard development of the shower. But if you orient the very same crystal, commercial crystal, you can reduce the length of the shower, making the calorimeter more compact, the detector more compact, with respect of the state-of-the-art detector. So you can contain the shower of particle above 100 GeV in a much shorter length. You can have a cost reduction, and in particular, you can find interesting application of this effect. But what I want to keep in mind, and that this happens in commercial available crystals. So in your calorimeters, if for some reason, so isotropic calorimeter, for some reason a particle is aligned at some point with the crystal axis, these effects occur. So one has to keep in mind that crystals are always crystals. We cannot treat them as amorphous. So we started our investigation choosing very quite known and cheap high-Z scintillator, so lectan state used for a CMS calorimeter and many other experiments. And we chosen also because it has a very simple crystal structure. It's a tetragonal structure. Two axes are the strongest one, A and B, and C is a bit weaker, but is also strength. And the strong fish threshold is around 30 GeV, but you can always have some effect even below. But already 30 GeV, this effect is microscopic, and we tested the 3 different samples. One is 0.45 radiation length, 1 radiation length, and 2 radiation lengths. So we did a series of test beam at extracted line of CERN SPS with 120 GeV electrons and positrons. So the energy means that we are in full strong field regime for this kind of crystal. So we have the beam, 2 silicon detector to measure the incoming divergence and track the particle. The crystal is coupled to silicon photomultiplier and mounted on a high precision goniometer to orient the axis with the beam. Then we have a multiplicity counter and a bending magnet sweep away the primary and the secondary charged particles, and only the neutral photon signal arrive at an electromagnetic calorimeter. So we started our investigation with the 4 mm long crystal oriented along the 001 crystal axis, and we see what we already have seen with germanium, a strong enhancement in the energy loss measured by the electromagnetic calorimeter. Keep in mind that how it is done, this setup, the energy lost in a secondary particle emitted inside the crystal cannot be measured by the calorimeter. So this is only the neutral signal. And we couple the crystal with commercially available silicon photomultiplier, and we measure directly the enhancement of the light output. That you see it peak at the double with respect to the randomly orientation, that is a blue one, and in axial orientation is a red one. So this is basically a demonstration that the shower is accelerated because you are measuring the enhancement of the secondary inside the scintillator. We try to do simulation because, you know, in Gen 4 all the materials are amorphous, even if they are not amorphous. We, in the past, developed a full simulation code based on Bayer-Katkov method to treat radiation effect in any kind of field, take into account the quantum effect of strong field. And we try to insert this full Monte Carlo, rescaling the physics list for Bremsstrahlung and pair production inside the Gen 4. It's not a simple way, so it's not so simple, but we obtain a good agreement with our experimental result. Through simulation, we can extrapolate all the information, because, as I told you, all the charged particles do not arrive at the calorimeters. But through simulation, I can extrapolate everything, and for the primary beam, it's like having a crystal with the 1.6 millimeter radiation length, so a reduce of a factor of 5 for the primary particle of the radiation length. And we obtain a ratio for the light output that is 2.2, that is fully compatible for what we measure with the silicon photomultiplier. Then in 2021, we did a second series of test beam with the other 2 samples of 1 and 2 radiation lengths, choosing the stronger axis this time. One was given us by the EMP of Minsk, and is a PVO2 that is doped with molybdenum, is the one chosen for the Panda calorimeter. The other one is commercially available from the Moltec company in Berlin. And we couple with a different board of silicon photomultiplier. So for the sample of one radiation length, we did a measurement with the calorimeter of different axial to beam orientation, try to find the range of the effect. So this is random orientation, the measure at the radiated energy measured at the calorimeter, and the blue curve is axial orientation, and this is 0.5 milliradians, 1 milliradians, 2 milliradians, but you always also see something different from random at 8 milliradians. 8 milliradians is half of a degree. So the range is small, but as I told you, not so small. The peak of axial case is smaller than in the case of 0.45 radiation lengths because more charged particles are produced and does not arrive at the calorimeter. So we started to do simulation with the thick crystal, trying to also insert the mosaicity of the crystal because this is not silicon, this is not perfect. So we measured the mosaicity of the sample that is less than 1 milliradian, so it's good, and we included it also in the Jan4 package. And we see a good agreement with simulation, so we can start to do prediction of what could be in future. So we have to fully finalize this package to in future to do prediction of what would be the results of a calorimeter made of oriented crystal. Then we see again the announcement of the signal of the silicon photomultiplier, and in this case the actual to random ratio is 2.5, and we made the same for the 2 radiation length crystals, and we obtain a factor of 3 of announcement. So it's clearly the shower is accelerated. And in macroscopic crystals, so even if they are not perfect crystals, they behave quite good in this direction. Possible application of an ultra-compact calorimeter made of oriented scintillators can be in fixed target experiments that are intrinsically forward. So you usually have few milliradians of range. In dark matter, search to realize compact active beam dump with increased sensitivity to light dark matter. In astroparticles, so you can point a telescope toward the source and reducing the volume needed to contain the shower started by gamma rays above 100 GeV. And keep in mind that if you are not in pointing strategy, your calorimeter still works in standard weight. So it's not 0-1. So if you are not pointing, it's even worse because this is a Fermi-Lat tower. You see there is you have a calorimeter made of crystal and you can think to orient them. We are investigating the possibility to make a small-handled calorimeter for the CLEVER experiment proposed as a successor of an A62 at Nordaria at CERN to investigate the decay of K long in pi0 nanobar. You have, with the small angle calorimeter that has a range, angular range of few milliradians, to reconstruct the pi0 coming from this decay, while any extra photons coming from the decay, for instance, of K long in pi0, be evaluated with very high efficiency, while maintaining sensitivity to more than 500 megahertz of neutral hadrons. So you need the ratio between radiation length and nuclear interaction length as smallest as possible. So you can use oriented crystal to reduce X0 while doing nothing to nuclear interaction length, and you need excellent time resolution, so you can use Cherenkov without. Possibilities are latent state, but also we are investigating a pure Cherenkov that is PBF2 crystals, and we can think about a matrix of crystal in which you need only the first few radiation lengths oriented, because it's at the beginning that the shower, when the energy of the particle is maximum, the shower is strongly accelerated by this effect. So we introduce briefly the strong crystalline field and how the shower is accelerator in axial-oriented crystal scintillator. And this has been done tests with commercially available sample. So this effect is macroscopic, and we measured the enhancement of light emission with crystal thickness and compare with Monte Carlo, in which we modify the physics list in Gen 4. So there could be possible application in particle and extraparticle physics, like Poynting strategy, high energy gamma telescope, beam dump, and fixed target experiment, like the clever small angle calorimeter that is the most straightforward now that we are collaborating inside it. But future work is test of Cherenkov material to realize ultra-compact and ultra-fast calorimeter, assembly and test a full calorimeter, not single crystal, and to evaluate fully the performances in terms of radiation length reduction and if the molar radius is modified and so on. Develop a full package in Gen 4 in which you can include the crystal structure of your material, and now we started a global fellowship about this to include inside Gen 4 this possibility. And after this work in the next year, we hope then ultra-compact and, if possible, ultra-fast electromagnetic calorimeters could realistically become fundamental detectors for future high intense and high energy physics experiment. So thank you for the attention.
Thank you very much. Question?
Thank you. Very interesting talk. I have one question to your measurements of the different light yield in axial and random direction. How do you ensure that there's no difference in light collection for the different geometries, which would then influence your light yield measurements?
Different geometry.
You turn your crystal, right?
But it's not so. It's not so macroscopic, because if you're at 2 degrees, you don't see this effect. So there is no such a big, cannot be explained by the big difference in the, so because at 2 degrees, the effect disappear basically.
Okay.
So you see an effective X0 which is much reduced. Does this also translate to reduced Mollier radius?
I think no. In our simulation, I think not, because basically does not affect the small energy secondary particles. So they.
Yeah, but you have more high energy particles, so the core should be narrower.
Yes. So we believe that the molar radius remain more or less the same, but no measurement has been done, and this is that is why I said we need to understand this. But we feel in our simulation, including the full Monte Carlo, but of course put something inside Giant, it is better to control. So we want to measure this. This is the next step.
More questions?
So thanks, Laura. Do I understand correctly that you don't use the crystal to measure the energy, but you use a different calorimeter to measure the energy? You just rotate a little bit, and this has an enhancement in Bremsstrahlung that you measure with an independent calorimeter.
Instead the light shield we measure directly cap into the crystals, and we are finalizing simulation to see which is the deposited energy, to connect the ADC signal to deposited energy. But we feel that the next measurement we are planning is to have a calorimeter around the crystal. So putting one of the sample inside a matrix, so it's covered by all the other crystals. So
in principle, yeah, you could use that as an alignment tool. I mean,
yes.
You connect something else, then you rotate, and where you have the peak on the other.
Yes, so the idea is that we already have like a 3x3 matrix of latent state coming from CMS end cap, and putting one of these crystals at the first and to rotate, and so we have the full measurement. So.
Thank you.
Okay. So then I think we can thank the speaker again.
Okay, so next speaker is Anna Stamella about the calorimeter from Muon Collider.
Hi everyone, I am Anna Stamerra, a PhD student at the University of Bari, and I will show you some of the preliminary results that we got in a simulation for an MPGD-based calorimeter for a Muon Collider. So I will start with a brief introduction on the Muon Collider motivations. Then I will talk about the beam-induced background that is one of the main challenges at a Muon Collider experiment. Then I will talk about our proposal for hadronic calorimeter and the R&D that is ongoing, and then show some of the results of the simulation. So the Muon Collider has great potentials, both in terms of discovery and precision machine. In fact, the European strategy for particle physics indicated it as one of the crucial tools for the development of the high-energy physics. This is because muons can probe multi-TeV energy range for discovery of new physics, and this because they do not suffer of synchrotron radiation at these energy values, and all the beam energy is available to the collisions. So for example, in the plot on the top, you can see a sort of comparison between a proton collider and a muon collider, and in particular, for a proton collider to reach the same pair production cross-section for heavy particle, we need to have a center of mass energy of around 100 TeV, whereas for a muon collider, it's enough around 14 TeV. Besides, on the bottom plot, you can see that X production is, the X particles are produced copiously, and therefore a Muon Collider experiment can gives precise measurements in the X sector. So an experiment at the Muon Collider has the basic structure of any other experiment at colliders. So there is a tracking system very close to the interaction point, then electromagnetic calorimeter followed by an hadronic calorimeter, a magnetic field provided by a superconducting solenoid, and the muon system in the outer layers. The current proposal for the HCAL consists of sampling calorimeters made of 60 layers of steel and plastic scintillating tiles. Our proposal will consist in replacing the active layer with micropattern gas detectors. One of the main differences with respect to other experiments relies in the shielding nozzles that are shown in this figure, that are very close to the interaction points, and they are needed to mitigate the beam-induced background. In fact, for example, from the simulation, we see that a photon flux of around 7.5 kilohertz per centimeter squared is expected at the surface of HCAL. However, for more details on the experiment at the Muon Collider, you can have a look at Massimo Casarsa's talk that he gave on Monday. So the beam-induced background is due to the muons, to the decay of the muons of the beam, and in particular to the interaction of the decay product with the machine elements and the detector of the experiment. And this constitutes the main source of background. The main kinematic properties are summarized in these three plots. So they, in general, beam particles have low momentum, a displaced origin with respect to the interaction point, and an asynchronous arrival time to the detector with respect to the bunch crossing. This is because, of course, this is due to the muons decaying before reaching the interaction point. Therefore, since we can actually exploit this characteristic in order to reject the background by using, for example, detectors that have high granularity and high time resolution. These are, for example, some of the requirements for the hadronic calorimeter at a Muon Collider. In particular, since high radiation is expected to the HCAL, we need a technology that is radiation hard. that can be produced in small size in order to offer high granularity and therefore high energy resolution for the particle reconstruction, and also a fast response to discriminate and to reject the background. Therefore, besides giving energy information on the particle that the particle released inside the calorimeters, we also need spatial and time coordinate for the reconstruction with the particle flow algorithm. So our proposal will consist in using MPGD for the active layers because they are gas detectors, so they are robust, intrinsically robust against radiations. They can be produced in small size and offer high granularity, and they have low cost with respect to other technologies so that they can instrument large areas of the experiment. Micro-pattern gas detectors has also the offer also high rate capability and good energy and time resolution, and they use environmental friendly gas mixture. Among the MPGDs, the best candidates are the state-of-the-art resistive micro-well and micromegas, because they also they can also mitigate the effect due to the discharge in the gas. So, for example, in micro-well and resistive micromegas, the latest development have shown that they can mitigate the discharge due to the high rate environment, but still have high rate capability. In particular, the gain stability has been tested up to 10 megahertz per centimeter squared for the micro-well and 1 megahertz per centimeter squared for the micromegas. Besides, the MPGDs offers high spatial resolution and time resolution. So now, coming to the design of the HCAL, we follow the strategy that starts with the simulation in Gen 4 in order to study the response to the hadronic showers. And in particular, in this talk, I will show you some results on the shower containment and on the energy resolution obtained with the digital readout. Then the parameters of the simulation will be implemented in the simulation of the moon, in the software of the Moon Collider in the context of the full apparatus, in order to study the impact on the particle reconstruction with the full apparatus. And then we will build an HCAL, a real cell prototype, and its performances will be measured in a test beam campaign. So for the Gen 4 simulation, we implemented the geometry that is sketched here. It consists in layers made of 2 centimeters of iron for the absorber and 5 millimeters of pure argon for the active gap to simulate the MPGD. Then each active layer is divided into cells of 1 by 1 centimeter squared to give the granularity. The shower response is studied using pion guns with different energies and using the physics list, one of the physics lists that is optimized for the hadronic showers. Then we try to optimize the geometry by varying the number of layers and the transversal dimensions of the calorimeter, trying to contain as much as possible the shower. In this plot, for example, you can see the containment, the longitudinal containment expressed in a fraction of average deposited energy as a function of the depth, of the longitudinal depth of the calorimeter, expressed in terms of nuclear interaction lengths for 3 different values of the pion energy. And in particular, you can see that the 19% of the energy is contained within around 14 nuclear interaction lengths. That corresponds to almost 100 layers in our geometry. And I just want to point out also that the 80% of the energy is contained within 50 layers of the calorimeter, that is around 7.5 nuclear interaction lengths, just because the energy resolution studies are performed in this configuration. The same study has been performed for the lateral containment, and in particular, considering the fraction of energy deposited in cylinders of increasing radius centered on the beam direction, on the pion direction. And here the fraction of energy deposited is expressed as a function of the radius of these cylinders in units of nuclear interaction lengths for different values of the pion energy. Here again, almost the 90% of the energy is contained within 3 nuclear interaction lengths. So before going to the energy resolution study, I just want to stress the fact that this study has been performed with simulating a digital readout. So the active layer has been divided into cells of 1 by 1 centimeter squared, and we defined one hit as one cell where the deposited energy is higher than 30 electron volts. That is more or less the ionization potential of the argon. In this way, the heat all have the same weight, so we do not distinguish between high energy and low energy heat, but it is one of the future plans that we are going to perform. So once we define the heat, we count the number of hit for each value of the pion energy, and from the distribution of the number of hit, we extract the mean value. Then we plot the number of hit as a function of the pion energy in order to find the calorimeter response function. And then from the inverse response function, we reconstruct the energy distribution in order to extract, again, the mean value and the sigma of the distribution. And then we get the energy resolution parameters by fitting a stochastic terms, a convolution of stochastic term with a constant term to the simulated data. So in the plot on the left, you can see some examples of number of hits distribution for different value of the pion energies. These distributions has been fitted with the Gaussian function, and the number of hits has been extracted and plotted as a function of the pion beam on the right plot. The response function has been fitted with different empirical functions, in particular power laws and logarithmic laws, and we choose the ones that offer the best performances for the energy resolution. Here on the left, you can see an example of reconstructed energy for a pion of 20 GeV obtained from the inverse response function of the power law. And on the right, you can see the energy resolution that has been fitted with the function shown there. And in particular, we got a 50% for the 6 stochastic terms and around 10% for the constant term. So then after the simulation will be performed and finalized, we will build a real cell prototype, and its performances will be tested in test beams. The design is still under development and will be adapted to low energy pions. Then the active layer will be instrumented with the state-of-the-art of resistive micro-well or micromegas. The readout will be performed using Fatigue ASIC that allows timing and charge measurement of the hits, and so it allows to emulate a semi-digital readout. The design, the construction, and the test has been comes from the effort of several INFN sites, Bari, Frascati, Roma 3, and Napoli. And then the test will be performed at CERN SPS with the pion and the muon beam to get the efficiency and the time resolution. So in conclusion, in these studies with Giant4 that I presented here, we showed some geometry optimization for the shower containment and the energy resolution studies. However, there is room for improvement, and in particular, we want to implement a more detailed geometry for the active layer by taking into account the material that will be introduced using MPGDs. Then we will implement the detector efficiency and the readout time windows and the semi-digital readout. And we will try to add neutron and photon background in order to simulate the beam-induced background and try to reject it from the real signal. Then the optimized geometry will be implemented in the muon collider software in order to test the performances in the full geometry, and a real cell prototype will be tested, constructed and tested. So thank you for the attention.
Thank you very much. So questions? Yeah.
And I have a question. For the containment of the shower, in your giant simulation, did you start the interaction always at the same point, or did you leave interaction free to move along the?
No, we started always at the same point.
Okay, because that's what it really counts in hadronic showers. It's the first where first interaction starts and the cascade takes place for containment.
Okay.
Other questions? Okay, if not, let's thanks to the speaker again.
Thank you.
So next speaker is Thomas Weitzman about the Epical2 Calorimeter Prototype.
Okay. Thank you very much. I would like to talk about a small prototype of done in the context of generic R&D for ultra-high granularity electromagnetic calorimetry. I will explain what I mean by ultra-high in the next few slides. So to introduce the concept, this ultra-high granularity allows us to do digital calorimetry. So the idea of this is to count the number of charged shower particles in sampling layers. And ideally, this would allow us to reduce the fluctuation from the individual samplings. If you're really able to count the particles, then you don't depend on the actual signal they give in the layers. We need high granularity for that due to the very high particle densities, in particular in a shower core. So we have built a state-of-the-art pixel calorimeter prototype. In fact, one already of quite a few years back, where you find a publication here where you can look up this one, the one I want to talk about today, the electromagnetic pixel calorimeter. That's where the abbreviation comes from. Number 2 is similar to the other one, a silicon tungsten stack, but now using more modern sensors, the Alpide sensors, which have been developed in the context of the ALICE experiment. And so I will describe this setup a little bit, and then we also discuss a little bit how we simulate in detail the detector. And then the main part of my talk will be about test measurements which show the calorimetric performance of this device. We have a detailed study from measurements at DAISY, so at rather low energy, but also first preliminary results from SPS for higher energy. This is a little bit of a busy slide, so it shows some of the details of this calorimeter prototype. The upper 2 figures show the single layer layout. So this is the design drawing where you have a tungsten plate, and then you have the Alpides, 2 Alpide sensors per layer, a chip cable to connect, and then a layer cable taking the signals out. And this is how this looks, in fact, in real life. This was constructed in Kharkiv in the Ukraine, which was a very important contribution for us. This was then stacked together, and here you see the design drawing of the full detector, and this is the actual detector before sort of further assembly with more cooling and stuff. So this contains 24 layers, each 3mm tungsten absorber and 2 Alpide CMOS sensors, and these ultra-thin flex cables, which in fact allow this very compact design, which leads to a Molière radius of the order of 11 millimeters of the full device. This is a sketch of the readout system. We read out by 2 layers of FPGA boards, because this is quite some, you have 25 million pixels in total for this small device. This is quite some data volume that we need, but I don't want to go into details of that here. Just a few photos from the test beam measurements. So this was our setup at DAISY. You see here the device, in fact, the cables going out to the left, and then the cooling in the right. And in the front, we have 2 little scintillators, which are exactly the size of the detector, 3 by 3 centimeters, scintillators coupled to SIPMs. Same setup with a little scintillator in addition here is at the SPS, just now facing a little bit the other direction. We've took data at DAISY between 1 and 5.8 GeV, and at H6 at the SPS in the range of 20 to 80 GeV with a mixed beam.
very important for this device is to really understand what happens microscopically. So we've gone to some effort for the simulation. So we do simulation with all-pix squared. This is a package that goes on top of a full Geon simulation, but it simulates the full charge transport in silicon. And here you see a little bit of the details. This is actually a part of a sensor. You see here the charge collecting diodes up here with a relatively strong field around the epitaxial layer. And then you see here, in fact, the tracks of charges that are transported in the silicon to the charge collecting diodes. This is all done in detail. And you can see also here 2 examples how nicely we can describe the behavior of the detector. So this is the cluster size distribution. So from as you see from all the charge tracks in the calorimeter, the data points are really measured, and the histogram is a simulation with this package. You see that out down to very large, to many orders of magnitude. This is very nicely described by the simulation. You should also note, like the dominant feature of clusters, of course, you get clusters of the average of cluster size 4, so 4 pixel hits, but very rarely there are extremely large clusters. And even this feature is nicely described. And here you see 2 examples of what happens sometimes in the detector. We think we really understand well what's going on here. This is in a single layer. Again, and you should see the scale is in millimeters now in this. And you see here a track that actually goes parallel to the sensor. In some cases, this happen rarely, but you do see this happen, and you see it happen in the simulation and in measurement in the very same way. So this is very nicely described. So we can use that also in comparing our measurements. And this is, of course, the earlier was just a very small part of a shower. Now this is a picture of single event display of a full shower at 5 GeV. So you see here a 3D view from the side. The color coding is the depth, so the layer number, in fact, the shower comes in from here, the electron comes in from here, and then showers in the detector. And here you see the different projections from the front and then from the 2 sides. So you maybe get an idea of what kind of information content you have that you can work on. And this is a low energy shower. Of course, you're significantly impacted by fluctuations of that, but once we look at the real high energy showers, this will be very interesting indeed. We've performed some calibration. In fact, the detector works out of the box without any calibration already reasonably well. But we can do additional calibration with muons. So we did this both with cosmic muons in the lab, but also with muons later in the mixed beam at the SPS, and those coincide very nicely. And here you see the different average number of hits in every sensor for muon tracks that we can identify in the detector. And you see variations of the order of 20%, and that is corrected so we have a calibration of the sensitivity of the individual sensors from that. At the moment, we still ignore within the in-sensor variation of sensitivity that might be there. We haven't even looked at that, so that there is a potential for an improvement if the sensitivity would be varying with position on the sensor. There's much less sensitivity to these variations in thresholds, where this comes from, in the number of clusters. So we have a clusterization to find, in fact, the equivalent of tracks, clusters of hits. There, of course, this varies very little, so this is much less sensitive to gain variations, in fact, or threshold variations. After this, this is what we obtained from the DESI measurements. So this is the 2 variables that we use for the response. So we can just count the number of fired pixels or hits, or we can count the number of clusters. Both are reasonable response observables, and you see nice Gaussian-like distributions. They're not completely Gaussian, they're details, but we can discuss in detail maybe after the talk if you're interested. But you see the behavior you expect, an increase with beam energy to higher, and the peak is relatively nicely again described with simulations. The simulation, in fact, I should say, is tuned to the 5 GeV point for the number of hits. So that's where the agreement is, of course, perfect. But all the other curves are also very nicely described. There's a little bit more of a deviation when you look at the cluster distributions, but that's maybe also because the tuning was done with respect to the number of hits. And the cluster algorithm we may have to further optimize. So this is now one of the main results I want to present. This is the response of the detector as a function of energy for both hits and clusters. You see a very nice, on this scale, this looks very nicely linear. And the simulation points here are, you cannot really distinguish from the measurements, so that nicely fits for both cases. Also shown here are in fact the results from our earlier prototype, which is a similar principle, but uses a different silicon sensor, the Mimosa sensor, which is much slower, and we had actually much more trouble, much more noise and problems with that at that point. But the absolute value of the number of hits is very, very close without any intercalibration between the two. So that's what you really get itself. Now we fitted this with a proportionality, with a linear function with the offset forced to 0, which we know is correct from the pedestal measurements, and that's the deviation from this linear behavior here. And here you see some hints of what you could call a nonlinearity. In fact, the simulation of the open points, the simulation for hits is very perfectly linear. So that seems to be in this respect, the ideal variable. You see a deviation of the number of clusters, and that is probably due to cluster merging. Already at this low energy, you will find some clusters which are touching, and our cluster algorithm then uses that or calls that a single cluster. And that will lead to a relative decrease in the amplitude for the higher you go in energy. Of course, the way we do the fit and force it to 0 causes this. It looks like there's a deviation to the upward in here, but in fact it's just a saturation when going high. The data now show a slightly different value, and we believe, and that is reflected by the error bars, that it is really explained by the existing nonlinearity in the DESY beam energy distributions that you get. That the nominal beam energy is not exactly, if you can find hints of that in a DESY publication on the test beam, and we discussed with the people, and this error is our best knowledge how to take that into account. But in fact, the nice feature is that the difference between hits and clusters is really exactly the same as in simulation. So we think we really understand this, and the genuine response of the detector is consistent with full linearity. And this, the next result I want to discuss is the resolution. These are two plots. The data points, the blue data points, are identical on the two plots. What you see here first is a comparison to simulation again. And then again, you see that maybe there's something about the properties of the test beam that we have to understand better. We have performed two simulations. So first of all, you see the general behavior you would expect, this 1 over root E dependence of the resolution. And you see the main feature that in this, the clusters are better than the hits, because apparently they take out some of the fluctuations that we do see. And then we compared the two sets of simulations. One uses the beam energy spread that is given in the publication by DESY as being constant as a function of energy for these test beams. In fact, we use a different test beam line than was discussed in that paper. And this is the open red symbols. And you see at the low energy, this even overshoots, but it doesn't really get the exact energy dependence. While if you take out the energy spread, of course, you're much too low. So we think, in fact, there is some energy spread which is maybe not completely understood here, and part of the deviation that we see in the data from simulation is due to this energy spread in the beam. On the right-hand side, we have a comparison of our results to our earlier prototype again, where the resolution was a little worse, and that was mainly due to the fact that we had like 30% of dead sensors in this older prototype. Now we have we have one dead sensor which is way in the back of the detector, so it doesn't really matter. And you see actually a nice improvement. In fact, the resolution for the clusters, which is the squares, is very close to the parameterization given from measurements with the Kali's physics prototype detector. Well, of course, it wasn't measured at low energy, it's slightly higher energy, but extrapolated down. Yeah, so it's nice that with a digital calorimeter now we get really very close to the state-of-the-art electromagnetic silicon, analog silicon tungsten calorimeter that is around. And then you can do much more. So we have only started to look in. Of course, you can do with the longitudinal segmentation. You can do longitudinal distributions. This is here for hits and clusters, and you see the shape you expect agrees again very nicely with simulation. We see, for example, I can't go into this, subtle details between the depth of the shower in hits and clusters, which is an interesting feature which we want to further explore. And then you can also look at the lateral distribution. So this, well, maybe first go here. These are the full lateral distributions at different depths of the detector, and you see a nice feature of a very narrow shower core in the early shower development, which gets broader and broader the further you go into the detector. And then you can combine this. This is both longitudinal. This is the longitudinal profile for different rings around the shower center, and you see here how the maximum of the shower shifts depending on where you sit in the core or in the periphery. This we can do much more on this, and this, as I said, it's just started. And for example, you can also do this event by event, of course. These are now average distributions, but there's a very high potential in there. Let me now briefly, for the rest of the talk, turn to first results from the SPS, and to what we can do with the detector is maybe also illustrated a little bit like this from this full spectrum of the mixed beam at the SPS. This is at 80 GeV, where we had a high muon component because we closed the collimator. So you see muons being produced from pions absorbed in the collimators. We can describe the hadron and muon part of the spectrum very, very nicely, and we see nicely that it's well separated from the electron peak here, which is very, very sharp. And there's extremely no noise in this detector. We've looked, this is very preliminary, we looked at the linearity. This is these old points I already showed before, and now this is sort of a out of the box, which we put the detector 1.5 years later again in beam. It worked like this. There was no further recalibration necessary between the two data sets. This very nicely. And this relatively mild nonlinearity, I think, also confirms that the stronger nonlinearity here is really due to the properties of the beam at DZ in this point. We also looked at the energy resolution that looks very nicely like. So in fact, this is now only from the hits, because the cluster algorithm we know we have to improve for higher energies, because there you get more cluster overlap because of the higher particle density, but the number of hits you can count. And in fact, the fit function here that we already fit to the lower data points is exactly the same now for high energies. So it's relates very nicely. We also expect that with clusters we will be better than that. So, but that has to be studied in the future. And then now, for the very last slides, I want to just demonstrate a little where one can go with the detector and what the potential is. Of course, this detector was, the idea for this, using this technology came from forward calorimeter in ALICE, where we want to separate close by photons, very close by photons. So now we simulated this in this calorimeter. This is now actually a simultaneous two-shower event of a 30 GeV and a 250 GeV electron at 1.2 millimeter separation. Where from the full event, if you know where it is, you can guess it. But if you, for example, look at the projection, the two dashed lines are the impact points of the calorimeter of the two particles. You see the high energy shower. You don't see the low energy shower. But now you look at you do a very little thing. You just look only at the first 6 layers in the calorimeter. The other was fully integrated, and then here it's hard to see here. This is again the integrated event display. But here then in the projection of these first 6 layers, you very nicely see 2 strong peaks. And this is 1.2 millimeters, so 1 millimeter separation is clearly possible. Maybe I think we can go down to a few tenths of a millimeter. So there's really where the potential is. This is simulation only for the time being. So let me summarize. I think we have proven that digital calorimetry works. We had shown this already with our earlier prototypes. We have confirmed this with the new one, which has a much better performance, which is, I think, essentially due to using the more modern sensor, the Alpide sensor, which has very no noise. And in fact, also the readout speed of that is compatible with modern experiments, so we can actually use that technology also in the ALICE experiment. We've seen we have good energy linearity and resolution. At the moment, the more detailed study is limited by the properties of the accelerator. We want to see what we can find out at SPS more. And then there's, as I said, there's extremely high potential for this for future experiments in general. If you think of particle flow, what you can do, single muon, should be able to see single muon tracks going through electromagnetic shower and take it out, things like that. So that is, but that we still have to do. So with that, I want to close with a slide of all the people helping here, and I would again like to emphasize, as a personal note, that I'm very happy that the LTU, this institute in the Ukraine, in Kharkiv, in a city where suffered very much, had a strong contribution here. And while we are enjoying here the nice weather, they are in a very dire situation. Thank you very much.
Thank you very much. Are there questions? Yeah.
So thanks for the nice results. Of course, you produce in a real calorimeter, you would have huge amount of data. How do you see a little bit the R&D needed on the data processing?
Yeah, I must admit we haven't really done anything on the problem that you would have in a full-scale calorimeter of this kind. What we want to do in the ALICE experiment is use 2 layers of this technology together with silicon pad, which is very similar to the CMS HD cal. In fact, we intend to use the similar electronics also, as you know. And then still with 2 layers, the data volume from the pixels is extremely high. So if you would want to go CMS or Atlas, that's impossible at the moment. In ALICE, what we find is that with the low particle density in PP and the relatively low rate in lead, we can probably do it. The Alpide has three, so you will get pileup, but the Alpide has 3 buffers for every pixel. So you can get, even if you get another event within the processing time of the signal, you can store it. And if you have like randomization of hits, then you should be able to get everything out. But it's in a full calorimeter, I think the way to go would be to have more intelligence on the chip and do some really on-chip, like taking a 1 by 1 square millimeter software pixel and counting the number of hits fired in that pixel and ship only that number, something like that. But,
yeah, please.
Yeah, very nice talk. I wanted to ask you this. In a very granular calorimeter, it has been shown that, in fact, the pattern of the energy distribution from a shower, in the case we studied was with muons, carries information on the energy, not just the total energy release. So in principle, if you can use a convolutional neural network capability at reconstruction level, you gain a resolution, you gain information. And I was wondering whether you have plans to study this on the front end or even, because you would like to do this online, because doing it offline requires you to save everything. And
yeah, but we have done some studies with this older prototype, which is the same principle, and the data is around for a much longer time. What you can do offline. So what we intend to do is to do a real 3D reconstruction of the shower, and then you use all the information from that shower to know about the energy. I agree that should be possible in a more simplistic way to do online, and we should explore that, but there's no manpower for the moment to do that. But it's a very straightforward idea in principle. To do it is another question.
Okay. Oh,
it's intriguing, the separation that you've shown between the 2 close showers, the 30 GeV and 20 and 50. Yeah, this is, of course, is simulation, but in fact, you do have data. It's separately for DAISY and from DAISY and SPS. Have you tried to overlap?
Yeah, that's the next step. We first want to understand clearly or well-defined single showers fully, and then we'll do that.
Okay.
Absolutely. No, we can do it with data. In fact, we do have, at DAISY, we even have measured pileup. So we have 2 shower, 3 shower, and even 4 shower events because we had high rate. So we can do it on real overlapping events even. And we can always get a good position resolution of the incoming shower from the first layer, which is before tungsten, in fact.
Yeah, thank you. I think we should go on. So thank you very much, speaker again. Okay, so our next speaker is Vincent Baudry about the prototype of the Caris silicon tungsten calorimeter.
Good. Thank you. Okay, so I will give you some recent results of our technological prototype of highly granular, not as high as Thomas, silicon calorimeter. So this is work from institute in France, Korea, Japan, and more recently Spain. So I will first start with giving you back the philosophy which is behind those technological choices we have made. So we are building calorimeters for particle flow, and the particle flow, we aim to measure charged particles by matching the cluster in the calorimeter with the track. And what is not often said, that we want to do that using only the spatial information in order to avoid to bring back the fluctuations from the calorimeter into the measurement. The aim at the end is to measure the best energy resolution for jets. And for that, so we use charged particles from the energy of charged particles from the tracker, and use only the eCalf to measure the photons, and 10% of the energy comes into neutral hadrons. What has come recently is also the timing information, could bring some information by the particle ID, and we have seen in the presentation from Torben that should be possible. This is something that has been put forward by the EGCAL. So the idea is 20 years old, but it's still evolving. So for the eCal that we are building, now the mission is to actually spot the tracks and showers in the calorimeter, and secondly to measure the energy of the photons and neutral hadrons in there with a timer of flight. This is something we are looking at. So the requirement for the eCal are the standard ones: hermeticity, resolution, uniformity, etc. But we add this very high granularity in the calorimeter, optimally for 500 GeV. So this is high energy. The optimal is 5 by 5 square millimeters, and of the order of 30 layers. If you go to lower energy, you can release a bit this criteria. For higher energy, like click or muon colliders, that should be even stronger requirement. We also want to have compact showers in order to separate them the best in compact jets. And those technical requirements then comes on the electronics and the integrations. We are playing with hundreds of millions of channels, and we have to operate them, have the electronics inside the detector, and of course it's heating, so we have to cool it. And we want to build also of the order of 100,000 boards with an optimal size that would be of the order of 1,000 channels per board. So this is the challenge. We think that for this challenge, the best is the silicon tungsten calorimeter, because we have a small molar radius, and we benefit from the flexibility you can have with the silicon, but also from this intrinsic stability. This is much easier to calibrate. From beam test to beam test, we see that the response stays very stable. The structure, mechanical structure, we've built one, so we know this is fine. The problem is to build the detector elements that will fit into that. And this is the program of CALIS. So that was our physical prototype from 2005 to 2011 that Thomas mentioned as comparison, where we had 1 by 1 square centimeters. And since then, we are working on this technological prototype in which we have the electronics which is embedded, which is power pulsed, self-triggering, and with a delayed readout, and which would aim at having a signal-to-noise ratio, which is the position of the MIP divided by the signal of the noise, which is above 12. So that's a bit of the challenge. And we want to build those boards here. Typically, this is the boards we have, so that they can be integrated into long cassette of the order of 8 boards, which are read out at a single end. So what I will be presenting today is the prototype here, in which you have 15 of those boards read out in a stack, which is more or less a tower of this later prototype. So I would say we are more or less at the middle of the way, but this is a logarithmic scale on number of elements we need to build. So those prototypes are built on this Skyrock chip, which is made by Omega. At the entrance, we have a preamplifier, and the signal is split into 3 branches, one with a fast shaping, which allows to make the trigger and the timing signal. And the 2 others are with 2 gains, of low gain and high gain, with a factor of 10 between the 2. And at the end, we store the information when we have a trigger of 3 branches, TDC, this high gain and low gain, and we have to select 2 of them. They are analogically stored and later digitized. So this is quite a complex chip. We have of the order of 600 configuration bits, but it has a low consumption, provided we can power pulse it with the ILC-like duty cycle. So we want to integrate 16 of those chips into our boards, and that's a long way to do that because we have many issues. The first one is that you have to put all the signals from one board to the next, and that's of the order of 140 signals going there. But and operate the chip with enough stability. And we also have mechanical constraints because you want the slab to be properly aligned. And we want to glue the wafers, the silicon wafers on it, and so you need a flatness which is good enough so that we don't break the wafers. So this is also a challenge for building those boards. So now we end up having 3 types of boards like this, with an evolution of this one. So here we have the chip which are packaged and glued on the board. That has evolved into this solution in which we have tried a different solution for connections. So this one, in order to make it compatible with, we need an adapter board here. And more recently, we have been able to make those boards working in which the chip are embedded into the PCB and bump bonded. So that allows you to have a much thinner design. At the cost of not being able to put any regulator or decoupling here. So they are harder to operate. And the most recent addition was reshuffling of the DIQ into a compact design, compact with the space available between the ECAL and the HCAL. That's about 30 millimeters. And this board here, which makes the readout of full cassette at the end, is of the order of 6 centimeters. So we are close to the design we want. And we can read 15 of those boards with a single board, on which we also have, and this is quite important for us, the full debugging system. So you see here online the beam spot that has been there, and this is a secondary beam spot due to the FEV13s, which are a bit shifted. That was not corrected on the online display. And here you see during the data taking, the shower profile by heat counting. So we went to DAISY in November 2021 and again in March. After 2 years of shifting, we had 3 test beams that were cancelled due to the COVID. And there we did mostly, commissioning and recording our first real showers into the calorimeter after so much time. So we had 2 configurations of the prototypes in which we have put a different amount of tungsten. The first one was okay for low energy particles, and then later we increased the amount of tungsten so that we can contain all the showers at the between 1 and 6 GeV at DAISY. The second run we ran together with the HCAL also. And we could do some run with and without tungsten, though the setup is flexible enough so that we can slide different tungsten in there. So you have some pictures here, the effective active area here, and the equally spaced by 15 millimeters of the layers. The first thing for those self-triggering devices is actually to tame the noise. We really have to be, we are sensitive to noise because we have limited memory space in the chips. And the chip is done so that as soon as you have one hit, you do the full readout of the 64 channels. So that gives you many noise channels, so you can study it. And one way to study it, a nice way, is to look at the correlations between all the channels and look what is the different causes of coherent noise. So this is a summary of all those measurements. So we have 15 layers times 1024 channels times 15 memory. So we have to fit all this. And one line here is a single ASIC. And you see that there are correlations. With the level of the pedestal, this is the pedestal level, is essentially coherent with the ASIC by ASIC. If you do this analysis of coherent noise, we end up with this figure. What you can see is mostly that we have a sigma noise distribution which is of the order of 2 to 3 ADC counts. If you have and this has to be compared with the level of the Mip, which is of the order of 70 to 140, depending on the thickness of the wafer. If you have a very sharp eyes, you will see that the noise will be slightly different in the different columns. They correspond to the different layers we have. And that corresponds actually to the different type of boards we have in the calorimeter. So this is the latest version of the board, this FAV13, where we have very stable conditions. That has integrated many of the experience we gained on those early boards. And this is the COP, the newest version of it, with we were really happy to see that it was working so well. Actually, we cheated a little bit because we had to put some coupling capacitors at some point to make them work. So they are not fully without decoupling, but we are really happy to see them working so well. If you look into the details of this noise map, so you basically see, here that this level of noise is ASIC by ASIC. Here, there are some global features, like here we have noisy power lines close to the acquisition board, and some channels we are repeating. This is always the same number of channels, and this is due to the layout of the board. So this is the kind of things we are fighting for. And we had to kill those channels because, as I said, the noise is really DNME if you have local storage into the front-end readout. So that's something that has to be monitored all the time and really be addressed. Once the noise is made, then we look at the Mip. Without the tungsten into the detector, we use the electrons as punch-through. And you see here the Mip spectrum for the FEV and the COB, and you see that they are very similar. Well, you see a little bit more the bumps here, but that's really some secondary effects. And we'll use this Mip calibration to, forgot that one. So this is the uniformity of the Mip calibration. So you see this is very nice, except for the channels that have been removed. So this is for FEV12, and this is for the latest board where FEV13 with thicker wafers, so we have highest response of the signal. What came as a bad news is that we have seen that some of our older boards started to have some problems. So I've drawn here the limit between the 4 wafers we have glued on each of the board, and you see that we are losing some of the channel on the side here. Maybe here, and we are suspecting this is due to the deformation or some stress there was during the transportation of the boards. So that comes really as a bad surprise, and we are investigating that to know why the gluing will not hold. So we hope this will not happen so soon with the other boards. But okay, that's an issue. So this calibration of MIPS we want to put inside to look at to do the simulation. So we use the ILC soft, and we have there a very flexible DD4HAP framework, on which we just change the XML configuration file and change completely our setup. And the digitization, this is ongoing work. We implement both the fast shaping for the trigger and time measurement and the slow shaping, and That's something we will add. So now this is not into the simulation I've shown here, but you see that even without this digitization, data looks very similar to Monte Carlo. You see the two showers here, very sparse. In the data, you still have some cells of noise in addition. And that can be used to compare the data which is in the shower. So this is the spectrum we see in individual cells for the full layers. So for the FEV13, we can go, you see the peak at 1 MIP, 2 MIPs, 3 MIPs, etc. And you can directly monitor the threshold, which is put at roughly 1/4 of a MIP. So we measure them very nicely, and that could be used also to do internal calibration in the detector with electromagnetic showers. This is with the highest gain we have with the chip. With the curb, this is slightly worse, but we still definitely see the nice MIP peaks, and we have a very, very nice threshold. And for the oldest one here, where we also were gluing the thinner wafers, there you cannot distinguish the characteristic of the MIPs in the showers. So the conclusion is that you can do in-shower calibration using this signal if you have good enough system. Last point we looked at was the saturation. So this is a shower profile. Here you have the layer numbers, and this is the response of the cells in unit of MIPS. So you have a peak at 1 MIP. This is just exactly what I've shown on logarithmic scale, and you can see that we are expecting signal up to 40 MIPS into the showers. And using the highest gain here, we have seen some saturation. So that depends really on the thickness of the wafer. The thicker, the earliest is the saturation. As I said, this is for the highest gain and in all mean by the detector. So to go to higher energy at CERN, 100 GeV, basically you have to scale that with the energy. We will saturate everything. So we go for lower gain. We have to divide it by a factor of 5 and see for this lower gain channel that has barely used up until now. So I will finish on the next steps. So we'll go for test beam at CERN in next month. We're integrating more of those new boards, removing some of the olders, put more tungsten so that we have full containment. And meanwhile, we are also looking on the finalizing the design of new boards that will also be more flexible with a better filtering of the noise for the high voltage, for example, and which are suitable for the chaining of the board up to 8 units. This is something I haven't shown anymore. So on the outlook, we are happy that we had our first 15 layers working properly. This is still kind of training phase. I haven't shown any resolution plot because this still needs correction of defects, the masking, etc. So that we have also the simulation and the data matching properly. But a month since the last data taking, that was too fast. And most of the layer are working as expected, but as I said, we have some sign of aging here. So that's something, one of of concern we are looking right now. So thank you for your attention, and I should mention the thank you for all the young people here that have been really devoted to the analysis. Not so young people, but also devoted persons. And thanks also for the engineering tool teams from our lab. They are really dedicated.
So thank you very much. And the questions? Everything is clear? Yeah.
So maybe just, I mean, you didn't show the energy resolution, but you could say a little bit about the sampling term and so on, what you...
Well, this has changed quite a lot. From the simulation, without without the decision, we go as low as 12%. But we know this is too optimistic. And the resolution, the first plot we've done, I don't show them because they're really, really bad. The thing is that we should shoot at some points where we have no defects like those masking cells, because the showers are very compact, and if you have all those channels which are masked at the same place, this makes a channel and really a hole in the distribution, and that degrades the performances. So we have to do a selection to see really the regions where we have everything working perfectly. That's
okay, but I mean, still it's interesting because in real big calorimeter with lots of channels, there are always a few channels.
Yes, so that's to complement also the discussion we had before. We are looking also at method where we would fit the 3D profile and we would jump over those noise cells and masking ones. But at the end, we know that with the newer version of the boards, in principle, we should have no mask channel. But okay, that's the challenge.
Thank you.
Any other questions? Okay, if not, let's thanks to speaker again.
You.
Okay, so I think last talk is from we conveners about the summary of the poster for the calorimeter sessions. So we cover
test, yes. Good.
So two conveners we will cover, and the first will be by Christophe Clement.
And then the second will be by you. So,
yeah.
Okay. So we divided, so we have the challenging task of summarizing the posters. So we split the task with Toshi Yuki. So we received 20 posters. We divided in a few categories that you will see up here. So I will skip directly into the material. So the first few posters we cover are about LHC, related to LHC and HLHC calorimeters. And also in between with the run-3 upgrade, which is still LHC. The first poster is about the CMS high granularity calorimeter. So we already talked this morning. This poster is more focused on the engineering challenges. So this calorimeter is rather complex, is occupying the same volume of the original NCAP calorimeter. However, it's actually more compact than before because some space was freed to introduce an additional muon layer. So the total thickness in terms of radiation length is still the same. You have challenges in terms of radiation damages, and the whole calorimeter will be operated at -30 degrees while you're actually dissipating 125 kilowatt per NCAP. So you see there is a lot of technical challenges, and then will be, you will see this on the poster. The next contribution is about the design and characterization of a fully functional FOCAL-E prototype in ALICE. So FOCAL is forward calorimeter, which will extend the scope of the ALICE experiment, and the E refers to the electromagnetic part of that calorimeter. So this new capability, which is actually not possible right now with ALICE, is that we allow you to do basically parton distribution functions down to x of 10 to the -6, which cannot be probed by any other experiment down to that. So it goes even beyond LHCb. And in particular, I will do this via prompt photon production. So here you need excellent photon pi0 separation in the forward region, and which leads you to this calorimeter system. So here you have a stack of high granularity and low granularity layers. And such a stack is being developed and tested in BEAM. So here there's results from SPS in 2021, where you can see the MIP. There are some uniformity studies, and there is a full demonstrator which will include additional parts of the electronics which are going to be tested in June. So you will get more detail on the poster. Let me move to a couple of slides on and posters about Atlas. So here is about the liquid argon electromagnetic calorimeter, which was upgraded for run 3, which is starting now. So essentially the world trigger path was upgraded. So we, in the original Atlas, the legacy Atlas, the calorimeter triggers were entirely analog. Now the liquid argon calorimeter is completely upgraded to a digital readout, which provides a huge improvement in granularity of what you can do at the trigger level. So you see the very, very coarse granularity in the trigger, in the old, let's say, liquid argon, and now what we have now for run 3, so you have layers, you can really do shower shape at the first level of trigger. So this is installed, this is running, and here you have already from the pilot run of October 21, you can see already some energy reconstructed in supercells, which are capturing also, photons from Bremsstrahlung, so you can reconstruct and compare with the fully offline energy. So it's just an example. The upgrade of the Atlas hadronic tile calorimeters. So the hadronic calorimeter of Atlas is mostly, the big upgrade is for HLLHC. It will also move to a full digital trigger, but only at the HLLHC. So this requires remaking the entire readout electronics. Also because of radiation harness, now we're talking even for hadron calorimeter, we are talking about 100 grays, which for the technology usually used for hadron calorimeter is challenging. So it requires a fully replacement of all the electronics and calibration systems, and you will find more details on Antonio's poster. Here is a poster which is focused on time calibration, monitoring, and performance. So this is also for the tile, so hadronic calorimeter of Atlas in run 2. I mean, we heard some calorimeters looking at timing on zillions of channels. Here is at the smaller scales, only 10,000 channels, already some challenge. You have several plots like this showing you a map of the quality of the timing. So the timing is very important because we are sampling the signal at 40 megahertz, and the energy reconstruction relies on the precise timing. And also because, of course, if you had more time, maybe you would to do the reconstruction, maybe you would be more independent on the timing, but because you want to do this at the trigger level very, very fast, you actually need to rely on the good timing. So you need to calibrate, you need a robust timing, you know what your need to know what your timing is, you need to find as soon as there is an outlier, there is a problem, you need to identify it. We have measured also the cell time resolution, and also you can use the timing here for finding non-collision backgrounds. So beam-induced backgrounds, there is a very tiny bit. It's not like the muon collider, but there is a little bit of it in Atlas as well, at LHC. Here is a poster which looks at the long-term aging of PMTs for high luminosity LHC. So the Atlas hadron calorimeter is using about 10,000 PMTs, which were installed at the beginning of LHC. And of course, at the end of HLLHC, these PMTs will be very old. So we have to ask our question, is that realistic? So here are some studies from the PIsa group showing the evolution of the current installed Atlas PMTs in the hadronic calorimeter. And you can see the response is falling down as a function of the integrated charge. So there is a numerical model developed which indicates that about 8% of the PMTs would lose so much during HLLHC that's not acceptable. And we need to replace them with a different type of PMTs. The PIsa group developed a precision test stand to do actually very long-term studies of the aging of PMTs, and have tested a new Hamamatsu PMT up to 500 Coulomb, which would then cover, I think, more or less the entire duration of HLLHC. The red ones are the current PMTs in Atlas, and here are the new PMTs which show very good behavior. Okay, moving on to particle reconstruction. So there is a poster about deep learning techniques, in particular to reconstruct photons and electrons versus jets in the CMS calorimeter. So you reconstruct the heats in the latent state crystals, then you cluster the cells together, and then you make superclusters because your photons will convert. They will emit Bremsstrahlung photons, so in the end, when you reach the face of the calorimeter, you have multiple clusters. And you need to group the clusters together to go back to the photon energy in a proper way. And if you do that in the bad way, of course, you will not measure the energy correctly. So right now, the current algorithm, there is a pattern in delta, in eta and phi, where you have this mustache shape where people decide, the algorithm decide to group the clusters together, but it's a little bit rigid. Here, there's a graph-based machine learning algorithm which was tested to do this grouping instead, much smarter and gives you actually improvement in energy resolution, immunity to pileup, and particle identification. Then here we have a poster which is looking at single particle uncertainties and local hadron calibration for particle flow in Atlas. So the idea of particle flow is, of course, that for low energy charge hadrons, you have the track measurements, which are very good, much better than the calorimeter, but the tracking is not measuring neutral particles. So you want to replace the energy from the calorimeter by tracks, at least up to a certain PT, and then remove that from the calorimeter and take the remaining, what's remaining calorimeter to, of course, model the neutrals. So for of course, what is the uncertainty on these processes? Well, it's very difficult to know what is the uncertainty on UJet energy scale and UJet energy for very high PT jets, because above 2 TeV, you don't really have, you don't have an in situ method anymore, and you don't have test beam, of course, and so on. So instead, what is done is to propagate particle per particle, so we know what's the response for single, let's say, hadrons, and then we propagate that through the whole chain and derive the uncertainty on the whole jet. What has been done in Atlas so far was not done on the particle flow jet, and this study proved that the same technique could be applied to P-flow jets. Here for the particle flow jets of Atlas, essentially the clusters which are included, they are calibrated at the EM scale. And I'm sure Nina can explain you more about the EM scale later on if you don't know about this. Here what you can do is you can check the characteristic of each cluster to determine whether this was more likely a hadronic energy deposit or more likely an electromagnetic deposit, and give it a weight. So this was done, used in Atlas before, but this has not been combined with the particle flow. What this plot shows is that actually there is some very promising results which could actually, combining the two, could help a lot the resolution. Okay, a few words about future calorimeters. So there is a poster about noble liquid calorimetry for future FCC experiments. So there is a very large range of very nice technological developments and simulations at various levels. So for example, okay, here you can see the electrode arrangement. The pre-shower is actually incorporated by just simply, I think, in the PCB itself. So I think it's the continuity in the PCB here. So very neat. Here, because now the number of channels is absolutely huge, but you still need feed-through for the liquid argon cryostat. So they are investigating connector-less feed-throughs, and I understand that they have found a solution. So connector-less feed-throughs. So I will probably ask later on exactly what's that. Also, so different electrode configuration have been studied to minimize the crosstalk. They have shown that they think they can reach a signal-to-noise ratio of 5 for MIPS per cell. They have been also looking at carbon fiber cryostat, which could decrease the amount of material in front of a calorimeter by a factor 10. Compared to aluminum cryostat, which sounds like amazing. And then, so in relatively conservative scenarios, they can have 8% sampling term. I think this scenario actually does not include the carbon fiber cryostat, so I guess that could be even better. And they also look at, for example, complicated tau final states. The Krylin semi-homogeneous crystal calorimeter for future muon collider. So here again, the big challenge at the muon collider is the radiation from the beam-induced background. So they're looking at the lead fluoride crystals, and in particular having 10 by 10 by 40 millimeters. Their prototypes have been built, like 2 modules back to back like this. Here you have a board with the silicon Pmts, the PMs, and actually, so they have put together a prototype of front-end electronics together with the CPMs, and pulse that with picosecond UV lasers and show that they could reach a 13 picosecond time resolution. Of course, radiation effects on the crystals was very interesting. So they actually here radiated So they expect about 10 to the 14 neutrons per square centimeter, and a TID of 10 to the minus 4 gigarad per year. So here it shows the effect. So they see the effect of 40% degradation on the crystals after 4 megarad, and actually no effect from the neutrons were observed at 10 to the 13 at least. Here this poster presents the high granularity scintillator strip electromagnetic calorimeter. So you have scintillating strips in 2 different directions to emulate an XY pattern. So you get XY coordinate in the 5 by 5 millimeter. A large technological prototype was constructed. So here you can see 1 detection layer, and here you can see the 30 layer assembled and integrated. So this has been characterized per channel. This all looks good. The calibration with LEDs were done. They can very nicely see the photoelectrons. You can also see so looking at cosmic ray showers, you can look at the lambda distributions. You here to see the shower. They have good agreement with simulation. They are investigating some trend of, it seems that the ADCs per MIP is decreasing slowly versus 3 months. So this is an investigation, but globally, this is a very promising and mature technology which has been fully built and integrated in a large prototype. And then finally, I think, so this is a test beam result from a dual readout calorimeter, so exploiting both scintillation and Cherenkov light in a way so that you can actually on shower per shower determine the M fraction. Which has a very, very strong potential for the future. So they have test results in electrons, and here you can see that they actually measure the calibration constant. I think it's, okay, doesn't matter, it's number of photons per GV, I believe, for the scintillation and for the Cherenkov, and it's actually very, very stable with the energy. So this is also very promising and a large prototype which was built. Okay, so now we move to the second part. So
okay, I will use this microphone to just minimize the transition time. Okay, so next I will cover the mainly 8 posters, like 3 for Mu2E and 3 for MEC2, and 2 are remaining for the other calorimeter applications. And the first one is the calorimetry for intensity frontier experiment. Namely the precision physics. So as we already heard in the morning session, this poster is related to the Mu2E calorimetry. And this Mu2E and the MEC2 experiments are related to the charged lepton flavor violating phenomena. And this is practically forbidden in the standard model. And that means also if we find any signal, this means the discovery of the new physics. So this is the rather actively looked for. And so this poster is introducing this calorimeter design and operation, and also the mechanical integrity into the Mu2E experiment. And next is the automated quality control station for the calibration of the Mu2E calorimeter readout unit. So this calorimeter uses cesium iodide, like 700 crystals, and this is read out by the silicon PMs. And this test station can monitor the, for example, the this one. Silicon PM gain and photon detection efficiency and charge at the different light intensities and bias voltages. And during this operation, this can be monitored, and stable operation could be checked. Okay, so this next is the design and assembly and operation of the scintillator-based cosmic ray tagger with the silicon PM readout. So basically, 2 plastic scintillator read out by CPMs are prepared to calibrate the Mu2E calorimeter by using a cosmic ray. And flat distributions are already obtained, and this zenith angle distributions are very good compared with the expectation. Okay, so next topic is about the liquid xenon MEC2 liquid xenon detector. And this, actually the MEG2 experiment already started physics data taking last year. And this MEG2 experiment, we look for mu2 gamma decay. And the gamma ray is detected by a liquid xenon gamma ray detector. And this poster mainly discuss about the timing resolution of the liquid xenon detector, but also including this other energy and position, performance are also described. Okay, so this top poster shows the liquid hydrogen target to fully characterize the new MEG2 liquid xenon calorimeter. And to calibrate this liquid xenon detector, the most important calibration will be the liquid hydrogen target plus a pi minus beam, which produces a charge exchange reaction, and the pi zero calibration. Pi zero will decay into 2 gammas. And this, if we select the back-to-back gammas, then 55 MeV gammas can be used, which is very close to the signal energy of the 52.8 MeV. So this is a very important calibration. And this poster describes the hydrogen target preparation. And this, actually, this charge exchange reaction calibration was already done last year. And this hydrogen target was successfully operated during last year. So this describes the design of the hydrogen target and along with the stable operation. And this slide poster shows the liquid large calorimeters, the possibility for the rather future precision physics by using these large crystals and to get the ultimate energy resolution and so on. And currently, this lanthan bromide and or LYSOs are investigated, and this simulation and with also the prototype test was already done, and this possibility for the future experiment is under investigation. Okay, so I move on to the remaining 2 topics about other calorimetry applications. So first is looking for a Cherenkov light in the liquid xenon with the light-only liquid xenon. So this project will try to disentangle scintillation light and Cherenkov radiation in a liquid xenon. And if we can detect both scintillation light and Cherenkov radiation, for example, for Nexo experiment, we may be able to distinguish the background from the 2E signal from the 1E background. Because if we, for example, select the direction by using a Cherenkov light, this can be distinguished. So to check this, both scintillation and liquid xenon scintillation light, these filters prepared in front of the CPMs. And one is only to select the liquid xenon scintillation light, like 175 nanometer. And for Cherenkov light, long pass filters are used to select larger than 220 nanometers. And the very preliminary result already shows some excess of the non-liquid xenon scintillation light, and this will be approved by a more sophisticated test chambers. Okay, so I think this is the last application, and this will tell us the study of the CPMs for calorimetry applications. And this is also a rather general purpose, and by using this electromagnetic calorimeter laid out by different light guide styles and also the PMTs and different CPMs. And to get the best performance of the, for example, light yield and efficiency and so on, so different materials will be tested for this application. Okay, so let me summarize this summary. So higher granularity, a better timing resolution, and radiation tolerance, and the readout electronics are essential for higher luminosity to ensure a good performance. And calorimetry plays a central role, not only for the collider experiment, but also for the intensity frontier experiment. So let's go to the poster session. I think the time is rather limited, but yeah, let's. If you are interested in, you can just go there. And yeah, this is the end of this session. But yes, so thank you very much for joining this session. Thank you. And I'm pretty sure you have some information.
Yeah, just a short announcement. So yeah, now there is some time to go to the poster session, and then for people who go to Pianosa, the bus is leaving at 11:30 from the usual spot up here where the buses are leaving. The other excursions, people have lunch here, and then this,